So, last class I have solved two example problems. One is for infinite beam, another is for the semi infinite beam. Now, today I will discuss the other cases for semi infinite beam, and before I start the semi infinite beam part, because I am giving the expressions for few loading cases, those are very common. So, these expression I have already derived, and you should also remember these expressions, because these expressions are very common. So, that is why I am given these expressions, or you can say these loading are very common. So, this is the infinite beam subjected to P. So, the concentrated load P is acting for infinite beam. So, y is equal to, y is the deflection, P lambda by 2 k into a lambda x, and theta or slope is equal to minus P lambda square by k into b lambda x, and bending moment is P by 4 lambda c lambda x, and shear force is minus P by 2 d lambda x. Now, for clockwise moment m, concentrated moment m, the expression of y is equal to m lambda square by k b lambda x, then theta is equal to m lambda cube by k c lambda x, then moment is equal to m divided by 2 d lambda x, and shear force is equal to minus m by 2 lambda a lambda x. So, these expressions I have already given. So, but I am writing all the expressions, all the important expressions under different loading conditions, those are very common. So, that is why I am writing all the expression in one particular place. So, that means here these expressions are valid, all these expressions are valid for x equal to greater than 0, that means for right side to the loading. Now, for uniformly distributed load or UDL, suppose these all are infinite beam. So, uniformly distributed load. So, this is the UDL whose intensity is Q, one end is A, another end is B, and I want to determine the all these quantities at a point inside the UDL. So, then the expressions will be the deflection at point C is equal to Q by 2 k 2 minus d lambda A minus d lambda B, and slope at point C will be Q by 2 k Q lambda by 2 k A lambda A minus A lambda B. Similarly, MC is Q by 4 lambda square, then B lambda A plus B lambda B, and the QC is equal to Q by 4 lambda Q by 4 lambda and C lambda A minus C lambda B. So, these equations I have derived. So, but I have derived only one case when the point of interest is within the UDL, but there may be a possibility that the point of interest may be the outside of the loading. Okay. In such case, suppose this is my case 1, similarly for case 2, your point of interest. So, this is the same UDL. Okay, this is also A, this is also B. Now, the point of interest is at here C, which is at a distance of A small a from point A and small b from point B. Okay. So, this is the same Q. So, in such case the expressions are that I am giving the expressions only y c is q by 2k d lambda A minus d lambda B, and then theta c is q lambda by 2k A lambda A minus A lambda B. Then m c is equal to minus q by 4 lambda square B lambda A minus B lambda B. Okay, and q c is equal to q by 4 lambda C lambda A minus C lambda B. Okay, so this is the expression. Now, there is another case, case 3, when the point of interest is right side to the loading. So, this is the C and this is B point, A point, C is at a distance of B and at a distance of A. So, this is Q. Now, in such case the y c value is equal to minus q by 2k d lambda A minus d lambda B. Then theta c is equal to q lambda by 2k A lambda A minus A lambda B. Then moment at C is q by 4 lambda square, that is B lambda A minus B lambda B, and shear force at C will be q by 4 lambda C lambda A minus C lambda B. So, these are the expressions. So, why I am giving these expressions only? Because these are the common, very common loading conditions, the concentrated load, concentrated moment and the UDL. So, there are other loading conditions are also, for example, the triangular load, but here these are very common. So, that is why if you know these expressions, that is good enough to solve problems, because most of the cases loading conditions are concentrated load, concentrated moment and UDL. So, that is why I am giving the expressions for all these loading conditions, and you should remember these expressions, or you should know. So, these are the expression by which you can determine these values. Now, I am going to the semi infinite finite beam other cases, because I have solved only the semi infinite beam where it is a free end. Because now there are other ends conditions also, that means that is free end is one condition, then the hinge end is another condition, then there is a condition of your fixed end also. So, now I will consider the next condition, that is beam with hinged end. Okay, so, that means here this infinite beam, this end is hinged and then a concentrated load P is acting. So, what is the boundary condition in such case? So, the boundary conditions or the BC will be that deflection at point A, boundary condition at A, the deflection will be 0 and it is a hinge end. So, moment will also be 0. So, we have to produce the end conditioning forces such that the net deflection and the net moment at hinge end will be 0. Okay? Because same as the free end condition, here also we will consider the beam as the infinite beam and we will determine the deflection at point A and the bending moment at point A, that will those will induce due to the external load P, and then we will apply the end conditioning forces and we will make the deflection and bending moment at the hinge end will is or are 0. So, but we know that the as I have already given this expression, the deflection at any point due to load P is P lambda by 2k into A lambda x, and due to moment the deflection will be equal to m 0 by k lambda square B lambda x. Okay, because I have given this expression, this is I am putting this is as a m. Okay. So, these expressions are given. So, this is the deflection m lambda square by k B lambda x. So, m lambda square by k B lambda x. So, these are the four deflection will develop due to the P and any moment m. So, I can write that the deflection at point A, that is the end conditioning, we have to apply end conditioning forces to make the deflection at point A 0. So, that means this will be equal to P 0 lambda by 2k. So, this is equal to 0, because here the y A is the deflection due to the force P and P 0 is the end conditioning force and m 0 also the end conditioning force. So, the deflection due to these three cases, that means why I am not considering m 0, because it is B lambda x which is 0 and this is the point x equal to 0. So, that is why this m 0 part will not come into picture, because we have applied the end conditioning force P 0 and m 0, and then we will get the deflection due to P 0 and m 0 at point A as well as the deflection due to the P. But here m 0 is not considered, because m 0 part will be 0, because B lambda at x equal to 0 is 0. So, this is one condition. Similarly, now the moment is another condition. So, m A, then the bending moment due to this P 0 will be P 0 4 lambda plus m 0 by 2, that is also equal to 0. So, you can see the bending moment is m 0 by 2 and this is P by 4 lambda. So, this is also P 0 by 4 lambda m 0 by 2, and why I am not taking the coefficient part, because coefficient part will be 1, because this is x equal to 0, this point is x equal to 0. So, here all the coefficient will be 1, A lambda x will be 1, C lambda x will be 1, D lambda x will be 1, but B lambda x will be 0. Okay. So, this is the m part, and then finally, if I solve these two equations, I will get P 0 is equal to minus 2k by lambda y A and m 0 is equal to k by lambda square y A minus 2 m A. So, this y A and m A are the deflection and the moment that will induce in an infinite beam due to the external load P, okay, at the hinge condition or hinge end. So, that the similar way that I have solved the free end semi infinite beam problem. So, this way we can get the expression of end conditioning forces P 0 and the m 0. Similarly, if we have a beam with a semi infinite beam, I should write the semi infinite beam . So, here semi infinite beam with fixed end. This is the hinge end, this is fixed end. So, this is the end condition, and here this side is infinite, here also this side is infinite. So, this P is acting. Okay. This is the point A. So, what is the condition? The condition is at A, the boundary condition are, this is the fixed end. So, deflection at A will be 0 and slope at A, that will be also 0. So, deflection will be at A will be 0 and the slope at A will be 0. Okay. So, the equation I will get the deflection due to the load P, then again there will be end conditioning forces P 0 and M 0, and again M 0 part will not come into picture, and then this will be the P 0 part, P 0 lambda by 2k, that is equal to 0, and theta A, then plus here P 0 contribution will not come, because this is theta is again B lambda x, and B lambda s at x equal to 0 is 0. So, this will not come, but theta contribution due to moment m 0 will come, and that is m lambda cube by k into c lambda x, which is 1 here at x equal to 0. So, that means I can write that this is m lambda or m 0 lambda cube by k, and that is equal to 0, because ultimately the net deflection and the slope will be 0. So, after solving these two equations, I will get P 0 is minus 2 k y a divided by lambda, and m 0 will be minus k lambda cube by and theta a. And remember that depending upon whether the point or your end condition is left side to the moment or right side to the moment, or the concentrated load or the any loading condition, because I have discussed the 3 loading conditions, and during the derivations I have given only the concentrated load. It is not true that only concentrated load will act. No, there can be a UDL also, there can be a concentrated moment also. For any loading condition you can determine the deflection or the bending moment or shear force or the slope, but here I have derived for concentrated load, but that can be any loading condition, and the equation I have already given. So, that means at any loading conditions you can derive the equations of P 0 and M 0 for different boundary conditions by the same procedure that I have discussed for the concentrated load P. Similarly, you can do it for the concentrated moment, you can do it for the UDL, because I have now given the equation if the point is outside of the loading, maybe the UDL, maybe the right side or the left side. Okay. So, that is the equations. Now, another thing I want to mention here, when I have given the equations for the UDL, for this first case, if you put A equal to 0 and B equal to L, suppose this is the length of the UDL L. Now, at point A, if you want to determine all these quantities, then put A equal to 0 and B equal to L. At point B, your B will be equal to 0, A will be equal to L, because now your B point, B and C will be the same point. So, that your B will be equal to 0 and A will be equal to L. So, remember that. Now, if you put B equal to 0, A equal to L, you will get in these equations you will get the deflection, shear force, bending moment and slope at 2 edges of the loading. Okay. So, now and then I want to mention that these equations, whether it is moment or it is load, I mean concentrated load, or it is UDL, depending upon whether the point of interest or the end is right side to the loading or the left side to the loading, you have to use the proper sign. Clear? Because the equations these are given for x equal to greater than 0, if it is the right side to the loading. If it is the left side to the loading, then you have to modify these equations that I have discussed. But in these UDL cases, all the 3 cases are given separately. So, you have to use the 3 cases depending upon its requirement or position or your position of the end or based on your point of interest. So, whether it is left side to the loading or right side to the loading or within the UDL, whatever it is. Clear? So, now the next one that I will discuss. Okay, so now one more thing I want to explain. I want to discuss that once you get P0 and M0, now you have to consider these two end conditioning forces and the external force or load or moment or UDL. Then you can determine these slope, deflection, bending moment and the shear force at any point you want. Okay, that the way I have solved the example problem for free end semi infinite beam condition, the similar way you can do that. So, now next one is that beam with finite length. So, okay, so this is beam with finite length. So, this is the similar type of procedure you will use for beam with finite length that we use for semi infinite beam. Suppose here also you have say UDL Q, or you can have the UDL Q and you have A point and B point. So, these are free end. So, this is also free end. Okay. So, because of this UDL, there will be a moment will develop and the shear force will develop. Okay. Here also moment will develop and the shear force will develop, and the boundary condition for now both the boundaries are free end. So, that means we can write that the net moment at point A will be equal to 0 and the net shear force at point A and B, I should write, is equal to 0. Here also A and B, because both the boundaries are free end condition. Okay, so, that means here because of this external UDL, there will be moment and shear force will induce at point A and B if I consider the beam as a infinite beam, but actually this is a free end beam. Both it is a finite beam with free ends. So, we have to apply the end conditioning forces. So, we have to apply the end conditioning forces P0 A and M0 A, here also P0 B and M0 B, such that the net bending moment at both the ends are 0 and the net shear force at both the ends are also 0. Okay. So, similar way you have to solve these equations. So, now I have discussed already the semi infinite beam solution. So, here I am not discussing this in detail this beam with finite length conditions, but the procedure is similar type the semi infinite beam, but only difference is in the semi infinite beam that is only one end is finite, another end is infinite, but here both the ends are finite. Similar way, if you have the both end hinge condition, then you have to apply the same boundary condition. Hinge conditions means if you have a hinge condition beam, that means the deflection at the hinge will be 0 and moment at the hinge will be 0, and then if it is a fixed end condition, then the deflection at the fixed end will be 0 and the slope at the fixed end will be 0. Similar way you have to solve this beam with finite length conditions. Okay? Because these conditions we will discuss when we will consider, we will model the pile as finite length beam, and then this concept we will use. So, that time I will discuss that using this concept how I will get the expression for lateral loaded pile to determine the deflection. But now these beam, whether it is the semi-infinite beam or the finite length beam or infinite beam. So, these problems can be solved in general way by numerical tool. So, I will discuss also that this beam with finite length, how you can solve this problem by using finite difference technique. So, next part is that beam with two parameter model. So, that means here beam on two parameter soil medium. That means, in previous cases beam were resting on the springs only, and as I have discussed that here there will be a connectivity between the springs as the beam is resting on the spring, but again the deflection you will get within the beam region only. So, deflections are confined within the beam region only. So, we will not get any deformation outside the beam region, but actually if I model a foundation as a beam. So, that means there will be a deformation beyond the foundation also in the soil. So, to get that deformation, we have to place or you have to model the soil as two parameter model, and then over that two parameter model we have to place the beam. So, that means here we have a two parameter medium. So, this is the two parameter soil, this is shear layer, with shear modulus G and which is thickness of H, then this soil is replaced as spring. Okay. Now, over this two parameter model, the beam is resting and over the beam there is the UDL say Q. Now, this beam can be infinite beam, this can be finite beam, this can be semi infinite beam. Okay. So, this is the problem. So, in the next class I will discuss or I will give you the expressions of this beam on two parameter soil medium, and then I will discuss that how these problems can be solved by using finite difference technique. Thank you.